Hello, it's Keith here, and this is the Simple series. Today we're going to be looking at the Atari 800 and 5200. They're basically the same machine, and we're going to be learning how to draw a simple little bitmap onto the screen. The idea being that if you're trying to write your own game, this could be a good foundation point just for you to get started quickly, and then you can make your own thing from that. So let's go over to the code and have a look at what we'll be doing today. So here's today's source code. This is the first version. There's two. The first one's going to do an 8x8 smiley. The second one's going to do our Chibico mascot at 48x48. There's two different files for that, but let's fire it up and let's just see it in action first. So here we have the Atari 800 version here. We've got a little smiley face. And if I just close this, and if we do the 5200 version, same file, could just compile on both, and there we have. It's rather small, but you can see the little smiley face there. So that's the first example, and let's go over the code and we'll learn how that was working. Okay, so in this example we're using some zero-page entries for various settings and things, and I'm defining them with this definition up here. Now I tend to mimic the Z80 registers when I'm doing this, so we've got these ZHL for high and low. That's going to be typically a source address, BC for byte count, the pair there, and DE for destination here. So we're just defining a few bytes for our use here. Now we're defining some entries that are going to be specific to the system. On the 5200, the GTIA is at C000. On the Atari 800, it's at D000 here. So we are just having to have a different version depending on our system. Now, once that's defined, we're going to be starting up our program here. First thing I'm doing is I'm clearing some of the memory because I was having some trouble with some things going wrong, and it just depends on the emulator and how the system starts up. So what we're doing here is we're just writing zeros to 255 bytes at the 0 page, and also clearing the GTIA addresses here. So that's just a loop wiping things out there. Next we're loading something called the display list. This is the definition of the size of the screen and the positions in memory that it occupies. We're going to have a look at it in just a moment. Once we've defined the display list, we can turn on the screen with the DMA control. We just write this byte combination here, which will turn the screen on. We're then defining the colors. Now the way that we define the colors is a little bit different depending on if we're using 2-color mode or 4-color mode. This example does support both. Now if we're defining 4-color mode, then we need to define obviously 4 colors. But if we're defining in 2-color mode, then actually the color is split into two parts, a brightness and an actual color. So we'd have a bright and a dark and a red, green, blue kind of thing. And rather strangely, the color part is actually shared between the background and the foreground. It's only the brightness that's used. But just to sort of clear things up, we're setting all of the palette entries here to the same color in this example. So this will set up the colors, and we're defining the background as black, the foreground colors as purple, cyan and white here. And the reason for that is that's the colors of our Chibico character. So that's what we're doing there. Now, that display list, let's find it. It's all the way down here. So this display list is essentially the definition of the screen. Now, the way the system works is that the graphics processor is running through the display list as the screen draws, and so it's reading in the line address in memory and then using that byte data to draw the line. We have to define this and tell the system what screen mode all the lines use. It may seem a little bit silly in this case because all of our lines are the same screen mode, but it does allow you to do tricks where different parts of the screen are in different modes. So you could have the top part of the screen very colourful for like a gradient or a sunset or something. The middle of the screen could be high resolution for some graphics, and then the bottom of the screen could be some text if you're making a text adventure or something. So it does allow a lot of power, but it's just a bit of a pain for us when we really just want a big graphics screen. Anyway, we just got to set it up here. So first of all, we start with 3 7-0s here in hexadecimal. That's got to be there. That's the sort of V blank at the top of the screen. Here we're defining the screen mode. Now we're either using screen mode E or screen mode F here for 4 and 2 colors. So you can see there's a definition here. And the first line, 40 plus screen mode, will define the start of the screen. And then we are specifying the memory address of the screen data. And our data starts at 2060. That's a good place to use for this example. We're then defining all the lines of the screen here. You can see the first half is here. But then we're having to do another screen mode definition and a new address. You see, we're having to start at 3000 here. The hardware itself will automatically increment the memory address it's reading from, but it will not step over that 4K boundary correctly. So we're having to manually do it for the video hardware. We then continue with the remaining lines, and then we've got the loop command here and a pointer to the display list jumping back to the top here. And we've got this right at the bottom of the cartridge, which is a fairly okay place for it to be. A B000 here, just a nice even place for the memory to be. Okay, so that's our screen defined, and now it's switched on. So we're going to be showing a bitmap to the screen. Now, where's our bitmap? Here it is. So we've got two different versions. The 2-color version is very straightforward. That's 1 bit per pixel. So if you look here, you've kind of got this round smiley shape here. And there's 2 zeros which make up the eyes, and the zeros make up the smile here. So it's a very simple format here. 1 is bright, 0 is off. So we're just defining the colors here. The 4-color version slightly different. We're basically using 2 bits for each color pixel. So that's how that's been calculated here. But we've got our bitmap here for the correct system. Okay, well, next what we're doing is we're calculating the screen address here. We need to be able to calculate a memory address within the screen buffer for an XY position so that we can work with the screen. So what we're doing here is we are taking an X and Y position here in the XY registers, and we are calculating the screen address accordingly. Now, the formula for our screen address is pretty simple. It's the base address of the screen, which is 2060, as we discussed before, and then the Y position times the width of the screen. The width of the screen is 40 bytes wide, and then we just add the X position. So we need to multiply Y by 40. Now, if you know about your 8-bit processors, you know multiplication is a little bit of a pain because there's no multiplication commands. So the fastest way to do this is by bit shifting. So you can shift all the bits to the left and it will double a value of a register. Now, we can't make 40 by just bit shifting. So what we're going to do is instead bit shift to make 32 and then bit shift to make 8 and then add those two together. And that's what we're doing here. So effectively we're multiplying Y by 32 with this part here, and then we're making Y times 8 with this part here, and we're adding the two together. So once we've done that, we then just need to add the X position, which we're doing just up here, and then the base of the screen 2060 just here. So it's a bit of a pain, but as I say, all of this code here is doing that multiplication via lots of bit shifts. It's of course using a 16-bit pair at all times. So some cases we're using the accumulator register as the low part of the pair here, just to save some memory because it's a bit faster than using a 0-page entry, but that's what that's doing. And that will allow us to select the correct location on the screen memory for the bitmap graphics that we want to draw. Okay, so we've got our bitmap, we've got our screen turned on, and we've got our ability to calculate a memory location. So now we've just got to draw the bitmap to the screen. So we're loading in the address of the bitmap data into the 0-page ZHL pair here. We're selecting an XY position. We're using that function to return the destination address in ZDE here, which is where we want to show on the screen. And then we've just got to transfer our bytes. So all we're doing here is we are loading in a single byte to the destination here. We're reading it in from the source, writing it to the destination, and then what we're doing is we are just going down here, and then all we're doing is we are increasing the memory address, moving it down one line by adding the equivalent of 40, hexadecimal 28 here, which will move the Y position down a line in the DE register pair. And then all we need to do is increase Y, which will effectively move us along 1 byte in the source data. And we just repeat 8 times, and that will draw the 8 lines of the smiley to the screen. And you did see that earlier. We'll just run it again. There it is. There's that smiley on the screen. Okay. Well, that's a little smiley. It's not bad, but it's hardly exciting. We do have a slightly more exciting example here with our Chibico character. There it is. It's a nice 48 by 48 2-color version there. And if we just remove this rem here, that will just turn on some Ucode. And there we've got our color Chibico. So that's quite nice. Well, the first question is, where can we get a valid graphic from? Well, if we just move this out of the way, what we have is Accu Sprite Editor. Accu Sprite Editor is my sprite editing tool that I wrote for these tutorials, and it can export into all the formats that I use in my tutorials, and it's what I use to create the bitmap data that I'm using in the example today. All you need to do is go to 6502, and we just need to select the Atari 5200, and you can see there's a Save Raw Bitmap 2-color and Save Raw Bitmap 4-color option here, and it will export this image in the correct format for today's example. Okay, so what's changed? Well, relatively little really. Obviously we've got a different bitmap now. We're importing the bitmaps with an ink bin. You can see there's 2 different versions, and coincidentally you can see that the Spectrum version is the same format as the example needs today for the 2-color mode. This is completely unchanged, as is this. This get screen position function. It's only this part that's changed here. This part's the same as well, but now here you see we've got a little bit more of a complex loop. So let's take a look at it. Well, just like before, we are using the loading of data from HL and storing it to DE, but this time we've got to go across the screen first, and then we've got to go down. So we're first using the Y counter to calculate across the screen, because we want to read in consecutive bytes and then write consecutive bytes, so Y is making a good counter for that. We repeat until we've done 6 bytes, because 6 times 8 is 48, and that's the width of our image in pixels. And then what we're doing is we're adding Y to the source address here, so that we move along the source by the number of bytes we've written. And then what we're doing is we're moving down the screen by hexadecimal 28, which is 40 again. Of course, DE never changed during this because we were using Y as an offset, so we don't need to do any kind of restore of DE here. And then we're just decreasing X, which ironically we're using as a vertical counter, but it's a more convenient register in this case, but it's a bit backwards. And then we just repeat until we've done the image, and that will draw the image to the screen. And that's all we need to do a bigger image. So there we go. I mean, it's not particularly complex to get graphics to the screen on the Atari 800 and 5200. The only tricky thing is getting that display list working, really, and hopefully this template example will give you the ability to do a simple graphics screen with relative ease. Now, the only problem with this example is it does use quite a bit of memory, but there's still plenty of memory left for me to do Grime 6502, so it should be okay for you if this is what you're going to use as your template. Anyway, I hope you found this example interesting. I've already got lots of other Atari 800 and 5200 examples, so please check out my YouTube channel for the playlist and see if there's anything else that interests you. As well, I've got lots of other systems, so if you'd prefer to do something Z80, 6502, or even now 8086, then, you know, lots more stuff out there for you. Anyway, whatever you do, I hope you'll enjoy programming the Atari 800 and 5200, and I hope you'll enjoy programming in general. Thanks for watching today, and goodbye.